When we specify the power of an electric load, we do this in the unit watts, and when our electricity bill arrives by the end of the year, we have to pay for kilowatt hours, which is the amount of energy we use up during the year. But how are electrical power and energy actually related to each other, and what do electricity and voltage and also resistance have to do with it? In this video I will explain this in detail, and I will also show you one of the most common mistakes when you combine the power law with Ohm's law. My name is Andreas from the Fearless Engineer, and here we go. Now let's talk about electrical power first. In one of the last videos on current and voltage, we have already talked about energy and about different forms of energy of charge carriers. If you don't know the video, here is the link coming up for you. And before we can define power in this video here, we have to take a closer look at the definitions of energy and of work. Now basically, for a charge carrier we differentiate between the potential energy and the kinetic energy. And the potential energy of a charge in an electric field can be compared really well with the positional energy of a body in the gravitational field of the Earth. Let's take this apple here as an example. The higher above the ground this apple hangs, the higher is its potential energy in the gravitational field of the Earth, although it makes no difference to the apple whether it hangs at a height of 2 meters or let's say 5 meters. But as soon as it falls from the tree, the difference becomes quite clear after a few fractions of a second. When it hits the ground, the apple from 5-meter height has a much higher speed than the apple from a 2-meter height. And from this we can conclude two things actually. The first is the potential energy of a body is converted into kinetic energy by the action of a force field. And the second is, for the conversion, it's irrelevant whether the body falls from a height of 20 meters to 15 meters or from 5 meters to 0 meters. The decisive factor is the height difference the apple falls. And the same is true for electric circuits. The mass of the apple here corresponds to the amount of charge, and the gravitational field of the Earth pulling at the apple corresponds to the electric field pulling or pushing the charges. And this means that, analogous to the classical equation mass times gravity times height, we can calculate the potential energy of charges as the product of charge times electric field times cable length. And with this we have established a connection between energy and two electrical quantities, that's charge and the electric field. But in order to come to a definition of electric power, we must first discuss the meaning of the term work. And when we generally talk about work being performed, we are usually referring to the conversion of a system's energy from one form to another form. For example, from potential energy to kinetic energy. And the work that is performed corresponds to the difference between the original form of energy before the conversion and after the conversion. And you can express this in a formula, for example, writing it as the work W equals energy after minus energy before. So when an electric field accelerates charges, their potential energy is converted into kinetic energy, and in the sense of energy conservation we can write this as E before equals E after plus E kinetic. And thus the work performed corresponds to the kinetic energy of the charge carriers. And if we now look again at the equation from the last video on potential energy, then we can already see a difference there, and this is the difference delta L. That is the equation, if you take it and look at it again, delta E equals Q, which is the charge, times E, which is the field, times delta L. And this exactly describes the work that is performed on the charge when it's moved by the field over a distance delta L in this case. And with this we are now clear on the terms energy and work, and we even have a first formula for it. And next let's talk about performance here. And generally speaking, performance is the ratio of the amount of work being done to the amount of time it takes to complete the work. For example, if you try to transport a bag of apples that fell from a tree in the energy example to a barn which is 500 meters away, you have to do a certain amount of work. And it can easily be seen that it makes a difference whether you need 10 minutes to do the job or if you need 20 minutes. And it is this difference between 10 and 20 minutes that is reflected in the concept of power. And by dividing work by time, we are saying that if we perform the same amount of work in a shorter time, the power is larger than if we complete the same amount of work in a longer time period. And the same applies to electrical power. If we compare two electric motors, the first of which has twice as much power as the second one, the first motor can lift a load twice as fast as the second motor, for example. That is, it has done the same work in half the time. And if we now keep the time constant instead of the work, then we can also say, for example, that a hairdryer with a power of 1000 watts converts twice as much electrical energy into heat energy as a 500 watt hairdryer. In other words, more power can one be used to complete the same work in less time, or two, to perform more work in the same time period. And if we now put the definition of work as power times time into our equation of potential electric energy, we get the following expression, which states that work equals charge times electric field times delta L equals power times delta T. And by the way, the time delta T here is the time in which the charge Q covers a distance delta L. And also W equals P times delta T is an important equation when it comes to your electricity bill, for example, and the money that you may have to pay back to your energy supplier by the end of the year. But more about that later, because now we have to first divide both sides of the equation by delta T and thus have a first expression for the electric power, which is P equals Q times E times delta L divided by delta T. And we have already seen in the video on current and voltage that the product E times delta L is also referred to as voltage U. And when we use this here and insert it into our expression, we get the following one, which states that power equals charge times current divided by the time it takes to move the current along. And in the same video, we defined electric current as the ratio of charge to time. And this means that we can now also replace the expression Q divided by delta T in our equation with the current I, and this is the amount of charge moving through the conductor in a given time. And with this we have found an expression for power, which states that P equals U times I. Power equals voltage times current. And this means that the electric power P is the product of voltage and current. The formula here is also called electric power law, and so we now know that it describes the conversion of potential energy from charges into kinetic energy in a certain amount of time. So the higher the power, the more potential energy can be converted into kinetic energy. And the unit in which we normally specify power is called the watt. And by the way, James Watt, after whom it's named, has improved the efficiency of the steam engine a great deal, and this is very fitting, as I see it, to the unit of power, which is named after him. And as an alternative to watts, the power can also be expressed in joules per second, or even as volt amperes when we refer to electric power. Now, the second part of this video here is about interpreting the performance law correctly when we want to analyze a circuit or component. For example, what happens to the power when we increase current or voltage, and also how does resistance fit into the picture here. And to understand this, we have to combine the power law on one side with Ohm's law on the other side. And I'll show you how to do this and also which error you should have to watch out for in practice. But let's first look at the law of power in its simplest form, that is the product of current and voltage. And if we measure the voltage that drops across a component and also at the same time the current that flows through it, then we know the power consumption of this component. At 0.1 amps current and 10 volts of voltage, we get with P equals U times I a power of 1 watt, which is converted by the black box you can see here. And as we have already seen, work means that energy is transformed from one form into another form. And the initial form here is the potential electric energy that is converted into kinetic energy, which is the electric field performs work on the charges, and when the charge carriers move through the black box you can see here, a conversion into other forms of energy takes place. And depending on which components are contained in the black box, this can be either thermal energy or light, for example, or electrical mechanical forms such as the rotation of a motor or the vibration of a loudspeaker membrane. But the energy can also be used, for example, to build up a magnetic field or to trigger chemical reactions. And as long as we don't know what is inside the black box, we can't say what percentage of the total power is used for which purpose exactly. And we can only say with certainty that the kinetic energy of the electrons is completely converted into thermal energy if we assume that our black box is a perfect resistor with 100% ohmic behavior. And if you don't know exactly what the term ohmic means, you can watch the video which I made about this topic, and you see the link coming up here in the cards. But if the black box is purely ohmic, then we can use Ohm's law to express the performance law in a different form. And this is how it works. Ohm's law states that the voltage drop across a purely ohmic resistor is equal to the current flow through the resistor multiplied by its value. So U equals R times I. And if we use this to replace the voltage in the power law, we get the following expression, which states that P equals R times I squared. So power is resistance times current squared. So we can also determine the power without the voltage in this case, that is by determining the resistance value and also then measuring the current, which of course assumes that R is constant and has been determined with sufficient accuracy. And we have already seen how to do this in another video. The link also is coming up here in the cards now. And as an alternative, we can also rearrange Ohm's law for the current, which is I equals U divided by R, so voltage divided by resistance. And if we insert this into the power law, then we get the expression power equals voltage squared divided by resistance. And this means that instead of measuring current, we can also measure voltage to determine electrical power. And in fact, an important conclusion can be drawn from the two equations here. As voltage and current are squared, this means that if we double the voltage or current, we get a quadrupling of power. And one of the most common mistakes in the interpretation of the equations is related to the resistance, because here the two equations seem to be somewhat contradictory. And with P equals U squared divided by R, a decrease of the resistance leads to an increase of the power, and with P equals I squared times R, it seems to be exactly the opposite way. But which one is correct now? And the best way to find this out is to perform a simulation. And in the left circuit, a resistor with a value of 2 ohms is supplied with a current from a voltage source of 2 volts, and if we use the power law, which is P equals U times I, to calculate the power converted into heat at the resistor, we arrive at a value of 2.0 watts. And if we now reduce the resistor on the right circuit by half to 1 ohm, then the power doubles to 4.0 watts. So in this case, it looks like the version P equals U squared divided by R is apparently right. But why is that the case? Now the answer can be found in the current itself. If we reduce the resistance by half, then the current increases from 1 amps to 2 amps, which is in the equation P equals I squared times R. The resistance has been reduced by half, but the current has doubled. And since the current is quadratic, we also get a value of 4 watts at 2 amps of current flow. And by the way, this only applies if the voltage does not change due to the changed resistance, which is we assume a so-called constant voltage source in the equation P equals U squared times R. And if we install a constant current source instead of a constant voltage source, the results actually look different. Let's take a look at the simulation here. The equation P equals I squared times R suggests that the power is reduced if we reduce the resistance. And in the right circuit, I have reduced the resistance from 2 ohms to 1 ohm, and you can see that the power is also reduced by half. So you should remember that when you have a fixed current supply, the power decreases with a resistor. And when we have a constant voltage supply, it's just the other way around. If we decrease the resistance, we increase the power that is converted within it. And the latter, by the way, is much more relevant in practice because most power supplies are fixed voltage sources and not fixed current sources. And we'll talk about both types of sources and the differences between theory and practice in more detail in one of the next videos, so don't worry if this is not entirely clear at this point in time. And finally, I have a very useful tool for you, which is a conversion circle, in which you can find out exactly how to convert the values current, voltage, and resistance and power into one another. In the quarter on the top right, you can see how to get the current with voltage and resistance, or power and voltage, or power and resistance. And on the bottom right, you can see the same for resistance, on the bottom left for voltage, and on the top left for power. So for example, if you want to calculate the voltage and you have the power and the resistance, then you can just have a look here and immediately see that you have to take the square root of the product of power and resistance to do so. And with this, you are now perfectly equipped to tackle some actual applications for the power law. For example, what power consumption and resistance an electric motor has, or what's the actual share of your mobile phone in your annual electricity cost. And as always, if you have questions or requests for topics I should cover here, just write me a comment down below and maybe I'll make one of the next videos out of your suggestion. And also, if you like this kind of video here, please consider subscribing to my channel, which will certainly keep me motivated to continue making videos like this for you. And also, you can download some of my learning materials such as slides and circuit diagrams or simulation files on my website at thefearlessengineer.com. So have fun and see you next time here on The Fearless Engineer.